Well, good afternoon, everybody, and welcome to today's webinar. My name is Rob Romanowski, Director of Sales Operations for 3HTI, and our presenter today is Rahul Roy. Rahul is a Service Applications Engineer from EnvisionTech, and as 3HTI, we are a systems integrator of various software and 3D printing technologies, for those of you who may not be familiar with us. So the way that 3D printers fits into our portfolio is with a lot of our customers in manufacturing that need either high precision results, a high resolution, or they need to print prototypes that will mimic aluminum or have the similar properties to metal parts. We also represent another line of printers called Mark Forged. But today, we're going to focus primarily on this 3D bioplotter from EnvisionTech. And I don't want to steal too much of Rahul's thunder, so I'm going to let him review all the wonderful details about this great system. So just a quick overview about Rahul. He has a Bachelor of Science in Biomedical and Medical Engineering from Rice University. And he has been with EnvisionTech over 2.5 years and has extensive knowledge of the applications for 3D printing and 3D biomaterials. So very excited that Rahul has the time to be with us today. The first thing I want to do, actually, before we get started, I almost forgot. I want to take a quick survey of our audience. I want to see what materials are you most interested in printing. So basically, in your attendance of this webinar today, if as we review this system and get into the details. Just wanted to see what your interest is and what specific materials make sense for you, because there is a wide range of materials that you can print with this bioplotter. All right, great. I'm going to close this poll. Thank you very much for voting. And one more just to check, which industry do you represent? We just had a local high school in Massachusetts purchase one of these bioplotters from us, and the reason that they purchased this bioplotter is because they want their school to be known as one of the schools for leading technology in the state of Massachusetts, which I think is very exciting and very forward thinking. All right, so I'm going to close this poll. Okay, and Rahul, you have control, so I'm going to pass everything over to you.
Fantastic. Thank you so much, Rob. As you mentioned, my name is Rahul Roy, and I'd like to cover a little bit about bioprinting. 3D printing is a 30-year-old technology, yet even today, it feels like the stuff of science fiction. Bioprinting in particular is featured in so many literary and cinema works, and I'd like to show you the advances in the field of bioprinting, moving us very closer to the very real future of medicine. Today we will cover a little bit about the basics of bioprinting, the applications that have been developed, some of the general materials, how these scaffolds are then constructed, and then some case studies to further illustrate how bioprinting has been applied, and even cover some details about our bioplotter in particular. And then I'd like to open the floor to questions. So, like non-medical 3D printing, bioprinting takes a raw material and layer by layer creates a construct, whether through a laser jet, an inkjet, extruder, or other types of methods, based on a stereolithography file. However, it goes a bit further because that construct can then be used, implanted in the body to regrow muscle tissue like skin, muscle, bone, or even corneas. The four major applications are drug delivery testing, which seeks to examine how a tissue will respond to a small amount of drug. The inpatient tissue regeneration, which is of course the most newsworthy of the applications. cell differentiation studies, which teach us how our body takes stem cells, uses signals like forces, chemistry, electrical signals, among others, to teach our stem cells how to go from those initial cell types to the somatic cells of our body. Then finally, pathology, the construct of how a tissue will respond when exposed to certain disease vectors. So in order to mimic these myriad tissue types in our bodies, we have to combine biocompatible materials. In general, these tissues can be categorized as hard and soft. Hard materials include thermoplastics for their strength but flexibility, ceramics, which are stronger than thermoplastics but not as flexible. But in addition, the body can actually recognize ceramic particles as signals to turn into bone. So that's the chemistry component, taking our stem cells and turning into body cells. And then even metals can be bioprinted, but of course these implants would not be for degradation. This would just be for custom small implants. Then moving to soft materials to mimic the numerous soft tissues in the body, we have synthetically derived hydrogels, meaning they are not pulled from any sort of animal or human source. And then the natural hydrogels, which already exist in some way, shape, or form in our bodies, and they are derived from animal sources, purified, and then can be used in tissue constructs. So then, whether you're using a hard or a soft biomaterial, we have to take it in their raw form and then solidify it in some meaningful shape. So with thermoplastics, you can heat them up, melt them down, and cool them. With hydrogels, there's many different ways of solidifying them through UV cross-linking, a two-part reaction, rapidly heating and then cooling them, and even freeze-drying them. Metals and ceramics must be held together with some sort of viscous binder, and then once the weak construct is made, you can sinter it or freeze-dry it in an oven.
Hey, Rahul.
Yes.
There is some background noise there, and we have a couple of people who are I think it's making it very difficult for them to hear you. I don't know if we can maybe take a minute and try to figure out maybe a better solution to reduce the background noise, because it seems to be coming through.
Yeah. Okay.
I know you're traveling, and I appreciate you taking the time to do this for us.
No, it's okay, certainly. So let's see, maybe I can actually step outside and try this. Sorry about that, folks. Thank you for your...
No worries. I think our group is pretty understanding. So while Rahul is getting set, thank you. Some of you are giving some nice comments about being understanding for Rahul's situation. So thank you.
All right. I've done something a little unconventional. Is this better?
That's a lot better.
All right, fantastic. I'm sitting outside the cafe, and let's see how this will go. Thanks, everybody. So do you all
Awesome.
need me to cover once again some of the previous slides? I'm more than happy to do so.
You know what? Let's do that. Let's start over. I got a couple people saying they're good. Let's just keep it going from here then.
All right, no problem. Yeah, and of course, I can just sort of rehash some of this in the very end if there's need for clarification. All right.
Absolutely.
So going to our, oops, jumped a little bit. All right, so with our thermoplastics, again, you can heat them up and then rapidly cool them to solidify. The advantage to using a thermoplastic with our bioplotter specifically is that you can actually blend them with other materials like the ceramics I previously mentioned, or even graphene, other temperature withstanding substances. So you can harness all kinds of properties besides just the strength and flexibility. For example, Northwestern, as I'm going to talk about later on, incorporated magnetic particles into their thermoplastics, allowing them to create flexible, strong magnetic constructs. With hydrogels, you can, again, use UV cross-linking. So at the top, you can see the, it's not important to know the specific compounds, of course, but you can see the general course of the reaction is you have a basic base chain, apply some UV light that acts on some sort of chemical group, and it binds together. The chemical reaction is a little bit tougher to visualize, so I have the diagram below. You create some sort of solution, including your chain of interest, in this case alginate. Sodium will disassociate from the alginate when you stick it in water, and then by incorporating calcium chloride, since calcium chloride can bond to 2 alginate chains instead of sodium binding to 1, you can then bind all of the alginate lines together. Rapid cooling is less of a chemical reaction compared to the other 2 types of processes, and tries to use intermolecular forces to bind the construct together. Same story with freeze drying, just the repeated heating and cooling of a construct in order to tightly bind all of the chains together. Then with metal and ceramic sintering, although the bioplotter is not capable of the laser-based sintering processes you might see in industrial scale machines, we can definitely create very strong metal constructs with our bioplotter, metal and ceramic constructs. By, again, suspending these metal powders into some sort of binder like methyl cellulose or polyvinyl alcohol, you're able to print out a weak construct called a green body. It'll certainly maintain its shape, but does not really have the mechanical properties to really mess with. But as soon as you put it inside an oven, the binder burns away and you can melt these particles together. Now, although I mentioned very viscous binders, again, the methyl cellulose and polyvinyl alcohol, later on I'm going to talk about a much better method of printing these kinds of constructs. So now that we have these general types of materials and the way that they solidify, we can talk a little bit about the shapes into which we are going to solidify them. You can actually arrange these materials in various patterns which will change the mechanical properties. So on the left-hand side, we have just a very basic 1 millimeter line with 90-degree spacing. It does the job of maintaining a certain level of porosity to allow us to introduce nutrients, growth factors, things of that nature, and also carry away waste. You can also increase the strength by incorporating triangles. So on the right-hand side, instead of a 90-degree orthogonal arrangement, these fibers are actually at a 60-degree arrangement. You can even change the spatial arrangement within a single construct so that one side of the object can be more rigid than the other, and we're going to see how that comes into play. Okay, so here are a couple of considerations now that we have these basic factors, our materials, the way they solidify, and the arrangements into which we can put them. Our constructs must be able to do the following. They need to induce tissue regeneration, which seems somewhat obvious, but this is where the cell differentiation studies come into play. We must understand all of the chemical, physical, and electrical forces that are involved in accurately developing our stem cells into somatic cells. We need to make sure that none of them interpret a signal incorrectly, for example, and then become an undesirable tissue construct. Biocompatibility. Not only must the basic chain that you're incorporating into the body, or whatever compound it may be, not cause the immune system to react negatively to it, but as the scaffold is degrading, it must not also create byproducts that then trigger an immune response. So it's not just the implant when installed, but the implant as it's degrading. Biomimicry. The reason that we are using hard and soft tissues in the first place is we need to make scaffolds that can adequately behave like the tissue that it is trying to replace until the tissue finally develops. So for example, with bone, it must match and not exceed or be less than the strength of the bone around it, because as it turns out, if your scaffold is too strong, the bone around it no longer experiences the correct forces, and the bone begins to degrade as it no longer needs strength. In addition, for example, in creating, say, a heart patch, you would want something that can stretch and contract just like the heart can without causing undue strain to the heart and not allowing the tissue construct to break. Degradation, again, we want the tissue to replace the scaffold instead of like a permanent implant where it completely goes away. Vascularization. This is particularly important in constructs greater than a 1 millimeter cube. As it turns out, if you create a scaffold greater than that size, without any blood vessels, the tissue will become necrotic and die. So even if you manage to make it as far as inducing the correct kinds of tissue, without that vascularization, that tissue will die. So we need to incorporate certain, say, growth factors or geometries that are conducive to creating those blood vessel networks that will then integrate into the body. Neurogenesis, in the same fashion, we want the body to not only know what is happening within the newly created tissue, but we need the tissue to communicate back to the body. And the best way to do so, besides the blood vessel network, is through the neurons. And so we need to, again, give consideration to creating neurons within the new tissue construct. So now I'd like to cover a couple of examples that'll cover the concepts that I just talked about and hopefully better illustrate these ideas. So in this particular paper, they examined the sustained delivery of tuberculosis drugs to prevent infection within a bone scaffold. So they used ceramic and beta-tricalcium phosphate as a strong bone signaling scaffold and then incorporated the tuberculosis drugs within the orange. And they wanted to make sure that these tuberculosis drugs were delivered at a steady rate. You wanted to make sure that the drug was always available, but you don't want too much delivered to the tissue at a time. And so you can see on the right-hand side, they were very successful in doing so. In this particular example, Shannon Backerich, her lab, wanted to figure out how they could adjust the mechanical properties of a particular tissue construct by alternating hydrogel and some sort of a UV curable adhesive. And by changing the proportions of each one, they were in fact able to create different kinds of rigidity, which have applications in replacing the knee cartilage. You can see in blue the rigid portions and then the flexible portions in red with greater concentrations of hydrogel. Another knee meniscus style study out of Columbia. This one incorporates PCL as a very nice flexible thermoplastic. It incorporates, again, some ceramic to, again, signal bone growth and increase its strength. But then they also go and spatially distribute growth factors. So the white portion has one type of growth factor, and then the blue has a different type of growth factor. And this was to examine if they could induce different kinds of cell differentiation across the cartilage. And they were, in fact, able to do so. The same lab took it a step further. And so they, instead of just spatially arranging growth factors, this time they actually spatially arranged the fibers themselves. And as it turns out, the body recognized the spatial arrangement of these fibers as itself a signal for different stages of differentiation. And you can see by combining both the spatial arrangement and spatial arrangement of growth factors, you are able to get better differentiation of cell types. Neither type of factor alone was as effective in creating good cell differentiation as having both the spatial arrangement of fibers and the spatial arrangement of growth factors. And then to sort of better illustrate the importance of vascularization, this is yet another bone scaffold using strontium and mesoporous bioactive glass. And by incorporating the strontium, they were actually better able to encourage both bone growth and vascularization than the bioactive glass alone. On the left-hand side, you have the control, in the middle, the bioactive glass alone, and then with incorporating the strontium, you have even further vascularization. Have I lost, do you guys still have connection to my presentation?
We absolutely do.
Okay, good. Sorry, it was giving me the notification that it was lost.
I see everything, so I think we're still going. Nobody has sent me any
fantastic
questions or saying, hey, where'd everybody go?
All right, fantastic. Glad to hear it. All right, and the final example, and this is very exciting because it represents a non-medical purpose or application, rather, of the bioplotter, and that is creating metallic architectures from 3D printed powder-based liquid inks, which is simply another version of the 3D printed metal and ceramic construct I mentioned earlier. This is a much faster method with higher loading than using a viscous binder, again, that polyvinyl alcohol and methyl cellulose. In this case, Shaw Lab from Northwestern used a little bit of PLA powder, some solvents, and then the particle of interest, and they were able to create highly loaded ceramic and then subsequently metal scaffolds by sintering these objects together. And here it better illustrates the process. On the left-hand side, you have the metal oxide powder. The addition of temperature with hydrogen causes the ceramic scaffold to reduce and shrink in size, and the non-metal portion of the ceramic construct goes away. And because this is a particle agnostic process, the lab intends to actually print out the periodic table. In addition to the periodic table, they were able to print out graphene. I don't have the demonstration here, but on our website we have a video where I plug in an LED to a graphene scaffold and it actually lights up. So with this presentation, I'd like to reiterate that clinical bioprinting is on the horizon. People are doing fantastic research to show that bioprinting is a real solution for understanding how we develop, creating therapies better tailored towards the individual, which will cause a faster recovery time and have less invasive procedures. On the research side of things, we can look forward to full-size organ printing in a cost-effective fashion. Surgeries, again, with minimal recovery time and no rejection, and even the next generation of pharmaceuticals. So with that, I'd like to open the floor to questions.
Excellent. Well, excellent presentation, and thank you for making the change because we could hear you a lot better. So anybody who has any questions at this time, feel free to type those into the question and answer box in your dashboard, and we'll answer those right away for you. I think it's kind of interesting, going back to something you were presenting earlier, is that you do have the ability to print metals using this bioprinter, bioplotter.
Definitely, definitely.
And I think
reiterate. Yep, go on.
And the technology is called a green technology because the material that holds the metal together will basically melt away when it's sintered.
Not quite. It's simply a green body. This is a carryover from, I imagine, metallurgy, just to indicate some sort of precursor structure or object that does not have the final desired mechanical strength. That's all.
Gotcha.
So it's just a green body.
Gotcha. So a question just came in. It says, are there any materials that are resorbable that you are familiar with, like collagen?
Sure. So collagen, hyaluronic acid, See, I believe I forgot the listing here, but I simply listed off some hydrogels that are commonly used. There we go. Yes, collagen, even agar, hyaluronic acid. These are just some of the natural hydrogels that are resorbable. The other types of hydrogels, rather than be incorporated, their byproducts are simply disposed of by the body.
Somebody asked a question about getting a copy of the presentation. So what I will do is I have this. We are recording this presentation today. I will have it uploaded in a link for everybody who attended, so you can watch it at your leisure. And I will also follow up with you as requested. We can set up a call with Rahul so we can go into more detail about what your needs are for this particular system and how we can help. I don't see any other questions in the queue at this time, so we're at the half-hour mark, so this was good.
Fantastic.
Excellent.
Fantastic. And of course, Rob, are you going to be providing your contact information so if they have any subsequent questions, they can certainly contact you?
Absolutely. I mean, absolutely. The best way that you that our audience can reach me is through the emails that were sent that I originally sent, inviting everybody to the webinar. You can respond to that. You can respond to that email. The other thing you can do is you could also respond to the emails that you receive from GoToWebinars notices. Or you can email me, and I'll keep it real simple. Info, I-N-F-O, @3hti.com is another way to get in touch with me directly. So thank you. I want to thank our audience. We have some nice compliments coming in. Rahul, you did a great job on the presentation. Very informative. So thank you once again, Rahul, for being with us today. Thank you, our audience, for being here. And our audience keeps thanking you. Awesome. So,
and Rob, thank you for hosting me, and thank you all, audience, for your time.
Excellent. Have a great day, everybody. Take care.
Take care.